Okay, let's have a crack at actually setting up. So we've got an equation of this form with this boundary condition here. Temperature, T is our temperature, we've got diffusivity, you've got a heat source you can add, and G is the boundary condition that we're going to define. So in the systems module in Underworld, there's a steady state heat object. Now this is the object that we're going to use, and basically what it does is it just pumps through standard Galerkin finite element methods, and it generates a big linear system. Once you've got your linear system, we can then generate a solver object, which will ask to go ahead and solve that linear system. So these are the steps. Okay, we'll create a mesh. Then we're going to create a mesh variable, which is going to encode your temperature solution. Then we need to define some boundary conditions. And once we have all that, we can actually go ahead and create our steady state heat object. And then create a solver and solve. So once again, let's create our mesh. Mesh. Let's stick with just the standard options there. They should be fine actually. And now let's just grab our temperature. Mesh variable. Okay, pass in the mesh. It's a temperature field, so it's just a scalar. Right. Now to the boundary conditions. So the idea with boundary conditions, we're just going to set it to Dirichlet boundary condition, which is a fixed boundary condition on the walls. The way they work in Underworld is you need to, in some way, capture the nodes that are boundary condition nodes, effectively. Once you've captured those nodes, then we create this Dirichlet condition object, which basically informs your system about the boundary conditions. And then we can just set the values we want on those boundaries directly via the data handle again. So the key point is that really this Dirichlet condition object is just flagging nodes as boundary nodes. Right? It doesn't actually set any values. You always just set the values directly via the data handle. And actually you can do that at any point. You don't need to do it after. The point is really that when the solvers, or when the steady state heat object is setting up the linear system, it gets to those nodes, they're flagged as boundaries, it goes, right, well, just use whatever value is already existing on those nodes. So how do we capture the boundary nodes? We do that, well, basically all you need to do is make a set of indices. The easiest way to do that is via these special sets that we have stored on the mesh itself, right? So if you look at the mesh and then you do special sets, it's a Python dictionary, right, of just special sets relating to that particular mesh. So when you have a Python dictionary, you can look at the keys for that dictionary just via the keys handle, right? So these are all the different special sets associated with that mesh object. So I mentioned earlier that when you're defining your mesh, you typically hand in a few tuples, one for the resolution, one for the min chord, and one for the max chord. So those tuples relate to each axis of your model. So we typically denote those as ijk, so in 3 dimension you have a k axis as well. And that's how these special sets are named. So this maximum I vertex set, for instance, is the set of nodes corresponding to the maximum position in the ith axis, right? So if it's ijk, or let's say 2D ij, let's say that I corresponds to x and j corresponds to y, for instance. So max I would correspond to the maximum x line of nodes, which is typically your right-hand wall, for instance. Likewise, min I would correspond to the minimum I left-hand wall. All walls grabbed all the walls. And then min j and max j will grab your bottom and top walls. Okay, so in this instance, we want to set a boundary condition of 1, temperature of 1 on the bottom, and a temperature of 0 on the top. So, anyone want to have a guess which wall will give me the bottom? Which special set corresponds to the bottom wall? Min J sounds good. So let's grab bottom set is, grab it just like this, mesh dot special sets. Now, again, you can hit tab to get your autocomplete. Will give you all your valid options there. What were we after? Was it Min J, and that's it. So we can have a look inside that guy. All right, so it's the node 0, 1, 2, 3, 4, which seems quite reasonable. Right, so just to convince ourselves of that 100%, what we can do is go for index in bottom set, and let's print mesh.data index. All right, so you can see y coordinate is always 0, what we want. And I just flagged here that there's a shortcut to doing that, and then we can just simply do mesh.data, and then we can pass that index set in directly. And that will just grab all the vertices corresponding to that index set. The only one trick is that you need to, again, the index sets themselves have a data handle, because the index set is actually an Underworld object to actually grab the underlying data, which is then returned as a NumPy array of indices. So we need to use the data guy there. And it also prints it a bit nicer for us.
John, if you wanted to leave one of those nodes out of the boundary conditions, can you do that? Can you manipulate that index set?
I think we can just actually remove it. Does this work? Let's check. Let's say bottom set dots remove. Let's say 0. All right. So now let's check what's inside that. Yep, 0 is gone.
And was that 0 as in the number, or 0 as in the position in the array?
0 as in the number. Yep. So if I do 0, that. Well, there's no 0 there, so I did 0 again and nothing's removed in that instance. 4, it will indeed remove 4. Yep. Let's refresh that guy. Now, what was the other set we wanted? The top as well. Let's grab the top set as well. Mesh.special sets, autocomplete, and we want max J. And just, there we go, that's the top guys. Right. Delete that for now. All right, just so we know exactly, let's have a quick look. Put on our node numbering. That's actually the other thing we can do with these node sets is we can just, they're all operator overloaded, so we can just add them together. So we can go top and bottom is equal to top set plus bottom set. Right. Let's have a look at this guy now. Right. So the only thing, just to finally 100% convince ourselves that we've got the nodes we want. Right, so we've captured 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, and 20, 21, 22, 23, and 24. Excuse the artifacts. Right, we've got the nodes we want. We can go ahead and create our Dirichlet boundary condition object. BC is equal to let's check what it asks for. It asks for the variable that it applies to, which is our temperature variable, and it asks for an index set per node, per degree of freedom. So in this case, we just pass in our all, what do we call that guy? Top and bottom. So when you get up to working in like a Stokes equation, you need to pass in an index set for each degree of freedom. So your vector field might has all your x direction velocities. You need to hand in an index set corresponding to what you want to do for the boundary condition for all the x direction velocities, and then a second index set for all your y direction velocities. We're just dealing with a scalar for now, so we don't need to worry about that. Right, we want to set our boundary condition values on the temperature variable itself. So we can do this a few ways. All right, well, let's just do it the quick way. All right, so we grab topset.data, and then we set that to 0 point. So again, we're grabbing the index set, and we're grabbing the NumPy handle of that index set. So now what we're effectively passing in here is a NumPy array of indices, right? And then we're grabbing the NumPy array of the temperature variable, and then we're setting that to 0 like that. Does that, anyone not kind of follow what I've done there? Feel free to shout out at any time if you've got questions, guys. All right, let's do the same on the bottom set. Let's set that to 1. Right. All right, I think we have everything we need now to create our actual system object, so let's do that one. So let's call it, let's just call it heat equation. Now it's inside the systems module, it's called steady state heat. Let's take a look at what it expects. So temperature field, we've got our temperature variable. A diffusivity function, we're just going to set that to 1 for now. Sorry? Shift tab. Yep, when you're inside the parentheses, hit Shift tab, and then it'll bring that up for you. And you can always hit tab as well, and for the regular autocomplete, but Shift tab is the one you're after. We're not going to provide any heating. We don't need to provide a swarm at the moment. So then we just need to provide our conditions. Note the syntax here. It's a little bit funny. So you'll be passing your conditions as a list, right? In this case, it's a list with one object in it, right? But you need to have this comma at the end to signify that it is still a list object.
So what was the initial temperature?
The temperature field is just the temperature mesh variable you've created.
Yeah, but the variable is for the initial temperature.
So
when you input in the steady state heat,
yeah,
temperature field?
Yeah, that's the variable that we're going to use to solve onto.
Okay, so it's where the solution is.
Yeah, that's right. That's where the solution's going. Yep, exactly right. Now, what's it complaining about here? Okay, I haven't set the diffusivity in the end, so let's diff 1, right. And we need a comma. All right. To create the solver, very straightforward. Again, inside your system object, in Underworld Systems module, there's a solver class there. You pass in the system of equations you want to solve effectively. I think our documentation is a bit lacking there. Heat equation. Right. Now we just solve. So we call the solve method on the solver object. Right. So let's take a look. very basic model, about as basic as they get. Any questions on that?
If you want to create a custom color map, you just send an array through colors equal to.
I think you can just do colors, and you could do something like this.
Yeah.
Blue. In fact, I think you can just go like this: colors, blue,
There's a pretty good
green.
help on that stuff, but it's in. You have to look at the views of the stuff. It's quite hard to find the help.
Why is this?